name is Jaitis John from the Department of Mineral and Geoscience, Malaysia, Sarawak, and I'll be chairing this session, which will run from 11 morning until 3:45 p.m. The moderator for this event would be Dr. Rauda Ahmadi, and there will be 6 talks, and every speaker shall have 20 minutes for their presentation, followed by 10 minutes for Q&A. And our signal will be used to indicate about 5 minutes and 1 minute to go with rings and a ring simultaneously. An audience can post questions via chat room for the session, and should time be running out, questions will be answered via manual correspondence. So before we get started, we will set our phone on silent mode. The next speaker would be Dr. May, and Dr. May is a senior lecturer at the Department of Civil Engineering in UNIMAS. He obtained a PhD in Urban and Environmental Engineering from the Kyushu University, Fukuoka, Japan in 2010, and he is actively involved with teaching and researches related to hydrogeology. And Dr. May will be talking about the assessment of subsurface condition of peat soil due to brackish groundwater seepage. As such, we would like to welcome Dr. May to give the presentation. Thank you.
Thank you so much for the opportunity. So first of all, could you hear me clearly?
Yes.
Okay, so first of all, thank you so much for this opportunity to present our cooperative work between UNIMAS and JMG Sarawak regarding the research of contaminant transport, salinity, groundwater salinity in Miri. So I would like to share my works with everybody. Hello.
Hello, Dr. May.
Yes.
Okay, now we can see.
Okay. So. Okay, so this today I'm going to present our collaborative work regarding the assessment of subsurface condition, soil, due to the brackish water groundwater seepage. Okay, so there are many. I mean, this is work done by our student, UNIMAS student, myself, and Mr. Ruslan, Mr. Jabri, and Mr. Edward in the GMG. Okay, so the discussion today will be related to, I will cover the introduction, why the groundwater, I mean, why this study is important, is necessary for all of us. Okay, and then after that, how this study was conducted. Then we go to result discussion, and finally conclusion and recommendation. the introduction. Why this study was formed? Because haze is a big problem in Southeast Asia, and in Malaysia there are many parts that affected by haze pollution. So Miri is one of them, because and then this place also close to Brunei, and it occur every quarter of the year, and the reason, I mean, the cause of this haze pollution is because of the burning process for the plantation. And another one is another cause is because of the smoldering process of dry peat after the opening burning activity occur. So where is this area? This area is in Kulabaram, somewhere around here. This is Miri. So Kulabaram is somewhere there. And then this is the haze pollution from the airplane. We traveled there, and then we can see from the airplane the haze pollution. This also, this one also. And then why this occur? Because in Kulabaram is peat cover most of the place. Big portion of the land was covered by the peat. And then how it look like? The peat is something like this. Okay, and then how does smoldering process look like? It's something like this. So this is the smoke after release from the pit. And then how the pit look like? So we visit one site during the drilling process. So this is the pit. You can see this is the pit, and this is also the condition of the pit over there. And this is the team during the visit. Okay, and then why this study important? Because what is the relationship between the haze and this study? Because in order to extinguish the haze or the fire, the water is important. So the water, they have two sources of water used to extinguish to put off the fire. So one is the surface water from DID, and another one is from the groundwater. And then from groundwater, we pump the groundwater from the aquifer and then release to the surface in order to release it to the drain, and then the drain will drain into the subsurface so that the smoldering process will not occur. So that's why the main objective of this study is we study about the brackish water, because the water that pump from the underground is a little bit brackish, mean salty. So this salty water will drain through the drainage, and then it will shift to the subsurface again. So that's our concern, because okay, so this is how we look like. We pump the water from the aquifer. This is a pumping process, and then this water will release into the drain, something like this. And then after that, the drain will the water in the drain will seep into the subsurface, and then it will extinguish this kind of smoldering process. And then our simulation is regarding to this one. Okay, so why the look at the quality of the water in the aquifer. So you can see that the average of the dissolved solids it's high. So the recommended dissolved solid usually around 700 or 800 milligram per liter. So this one is average already like almost 1000. This is second aquifer. This is the third aquifer. This one. So it's a little bit brackish. Okay. So what we do is our work is we collect the data. We collect all the data in that study area. And then the data will be collected, and then through the soil the detailed investigation, we go to the site, and then we try to collect from the secondary data, the groundwater property, the soil property, and also the drainage property, and then we do the modeling. So in the modeling, we establish after we collect all this data, we establish the conceptual model. That this conceptual model is it consists of several aquifer layer. You can see here. So the first layer will be peat. This is important part of us. The peat, and after that we have sand, we have clay. So clay is a little bit thick. You can see that's 48 meter. Peat more than 5 meter. Okay, sand is 11 meter, and after that we have fine and medium grain side. Grain sand. So this is the third, yeah, the third aquifer, and then after that we have clay. So our simulation, we focus on this one. You can see this one. It is a drainage actually. So this is a drainage. So we do the simulation all this area around 20 kilometer to 25 kilometer, and then we would like to simulate the water when the water flow into the drain, because this is the brackish water. So how the migration of those salinity will look like in the subsurface. So in order to do so, we look at the hydrological condition in the area. So the rainfall distribution over there is, you can see from here, this is the rainfall distribution. So this is 2. You can see the average month, rainfall in the area is around, maybe around 150 per month. And then the tool that we, okay, after we do after we successfully construct this conceptual model, so we do the assessment. Okay, conceptual model, we do the modeling, and then after it is successful, we do the assessment. So assessment consists of 2. We have one scenario 1, which is a natural condition. And we have another one is the second scenario, which is the drainage condition. So the tool that we use is we use the visual mode flow, groundwater flow simulation, visual mode flow for the groundwater simulation, and we use CWAT for the solute transport simulation. CWAT for the solute transport. So in this case, the salt. In our case, salt is our transportation. Okay. So so in this case, we do the, okay, so this is the condition, aquifer property condition. Okay, this is the aquifer property. So in this case, you can see that the peat here, the characteristic of the peat is we have hydraulic conductivity. The average is around 3.2 exponential 4 minus 4. This is we take the data from secondary data, which is the peat is in Johor and Selangor. And then we have fine sand. This is the average is around exponential minus 4. And we have city clay is minus 5. And then the grain, medium grain sand is minus 4, 2.5 minus 4. Okay, and then we have a recharge. So the recharge, we try this one, meaning that because we do the sensitivity analysis, so we try several percentage from the rainfall. Here the percentage here mean percentage from the rainfall, total rainfall. So this one is around 5%, 8, 10, 11, 15, and 12 and 15. So this is for the sensitive analysis. And then for the porosity, it's important because we do the solute transport. So solute transport require the actual velocity. So actual velocity is we we need actual velocity is equal to the dark sea velocity divided by the porosity. So we use, this is the porosity that we use in our study area. Okay, and then after we collect and construct the conceptual model, so now we run the simulation. So we get the result. So the result is divided into, we present about calibration. We present calibration. We present about the flow condition in the study area. And we present the breakage distribution condition. So calibration, for the calibration result, we have several well. Calibration means the comparison between the observed value, observed head mean the groundwater head in the well, and the groundwater head based on the calculated value. So we do the comparison, and then there are several wells within the study area. So we find that the coefficient R square that we get is around 75%, while the root mean square error is around 1 meter. So we have like plus minus 1 meter error, while the R square is 75%. So after we do the calibration and validation, calibration and sensitivity analysis, we get the, in here we don't present the sensitivity analysis, but in the paper we do present it. We we got the, this is the final property for the aquifer, for each aquifer. So this is what we get. So peat is around 3.2 minus 4. Fine sand is minus 4, clay minus 6, medium grain sand is minus 3, and silty clay is minus 6. Okay. While the specific storage is this value, the specific yield is 0.4 for the peat, fine sand is 0.3, clay very low, 0.06, and medium grain sand is 0.3. Okay, and so on. This is the porosity. Porosity, as I said, porosity is important because of the solid transport. We need to consider the porosity. So this is what we get after we do the calibration and sensitivity analysis. Okay, so now we move to the flow, groundwater flow condition. So groundwater flow condition in the study, our study area, you can see from here. So the this is the groundwater head. So the groundwater head is it changed from 10 to 0 meter above sea level, meaning that this one is around 10 meter above sea level, and this is a 0 meter above sea level because this is the sea. So the groundwater tend to move from the west here, okay, move from the west to the two direction actually, two direction. So one from the east, sorry, from the east to the northwest. This is this is a Baram River. This is a Baram River. This is the sea. So you move to the sea to move to the river as well as move to the sea at the northwest. And then another pattern of the flow is it moves from the east to the west. So this is another river. This is another small river. So, and then if you look at the condition, vertical condition, you can see that the groundwater mostly layer the peat soil, the clay and the sand. So usually the groundwater move vertically, okay, and in this the lower sand layer, so the groundwater move a little bit horizontally like this. Okay, and after that, we have a clay layer at the bottom. So mostly the groundwater is moved from the land, from the inland to the sea. So okay, so this is the condition of the groundwater flow in the study area. So mostly two direction. So what is from from east to northwest, and from east to west, okay, to the sea. Okay, groundwater flow is important. After we understand the groundwater flow condition, so now we are able to concentrate on the solute transport. So in our case, it's a breakage distribution. So the salt distribution in the aquifer. So in the salt condition, so we present here is this is a day one. So meaning that this is a time one that, as I said, we have two conditions in our methodology. So first is natural condition. So in here, the first time we use the natural condition, meaning that we simulate the natural condition in our study area. So how the salt look like. So the salt look like, meaning that now the in this area, because here is a sea. So here is a sea. So from the sea, the ground or the salt distribution is something like this. So it's close to the coastal area. The groundwater is a little bit salty. So here is very salty. And then after that, after one day, so this is the first day, doesn't have any problem. But we have this 2 years later. So 2 years later, you can see that if we allow the water drain into the if you allow the water, pump the water and drain and release along the drainage. So now after 2 years, so the water will percolate into the subsurface. I mean, the salt will percolate into the subsurface around this layer, third layer. So this is a peat, and then we have sand and clay. Okay, and then sand again. Peat, clay, sand, and then clay again, and then sand. Okay, and then after that, after 10 years, we can see that this is the movement of the salt or the breakage in the drain. So while the water in the sea doesn't move much. Okay, so after 10 years, after 20 years, we can see that here it move a little bit further, and then after 50 years, it move like this. So meaning that after 10 years, so the movement of this the salt doesn't have much. It is insignificant. So after 10 years. So we come to the conclusion that after we establish the conceptual model, we are able to model the migration of the breakage water into the subsurface through the drainage in the study area, and then the results show that only slight movement of the salt concentration. So meaning that if we talk about 1 year, 2 years, so the movement of the salt is not so great. Okay, it's not so significant. And then another thing is that the high concentration along the coastal the high concentration from the sea only concentrate along the coastal area. So meaning that doesn't have any effect from the pumping process, And then the salt concentration reduce as it move further inland. Okay, and then therefore the impact of breakage groundwater on the environment is not significant since the salt concentration is low in most of the study area. So we recommend that the further study should be on the crop, because actually the main purpose of this study is we would like to see the concentration distribution, and then how those concentration will affect the crop actually. So meaning that in the next step, we should concentrate on the concentration on the crop, the impact of the concentration, soil concentration on the crop. So this will help the plantation owner decide the best location for the plant, to plant the crop. So what are the best crop that is suitable for the plantation? And then another thing is so this is decide for the best location to plant the crop. And then another one is design drainage. Okay, design drainage that able to reduce the salt concentration before it migrate into the aquifer material. So that it is one of the best recommendation. So the selection of proper material is crucial when design the drainage system so that it will not pollute the environment. So this is another recommendation. Okay, so that's all. And then all of us would like to thank JMG Sarawak for support for the field, for field support and data support. Thank you so much.
Thank you, Dr. May, for your interesting presentation. And I'm very happy to know brackish water will not have any significant effect on the environment, and also the recommendation for the best crop for this area which is affected by this study. So without going further, I would like to ask for any questions from the floor. So you can write it down in the Q&A. So if there is no questions, probably floor can write into our to seek for further information about the maize paper. So with that, thank you, Dr. May, for your presentation. And
thank you so much. Yes.
the next will be by engineer Dr. Noraslina Sadon, who is a senior lecturer at the Department of Civil Engineering UNIMAS, and she obtained a PhD in the field of technical engineering from the University of Auckland, New Zealand in 2012. Actively involved in many research related to peat soil and problematic soft soil. Without further ado, we would like to welcome Dr. Noraslina, who will be talking about peat settlement observation in Sri Aman, Sarawak. Please, Dr. Noraslina.
Yeah, okay. Thank you, Chairperson. A very good morning to all. Is it the voice clear to all of you?
Yes.
Yeah, right. Good. So okay. Today I will present the findings that based on our collaboration works between Unimas and JMG Sarawak. So today I will share some of the findings. Hold on. Right. Okay, a very good morning. Assalamualaikum. Thank you, Chairperson, Mr. Jaistin John from JMG Sarawak. Okay, my name is Nur Azlina binti Muhammad Sadun from University Malaysia Sarawak. So basically, this paper presented is a collaborative work done between Unimas and JMG. So from Unimas team, myself, Dr. Duraza and Dr. Siti Nolinda, and from the JMG Sarawak team is Mr. Edward Anakmol, Mr. Benson Lin Jin Yao, and also Madam Angela P. So for today's presentation, so the topic is Sri Aman Peat, okay, settlement observation and geotechnical properties. So these are the outlines of the presentation, which comprise of the introduction, with a brief, or we can call it recap on definition of peat itself, and then we move forward to the site settlement observation in Sri Aman. We're focusing on Balai Bomba Sri Aman, and then we move on to the soil sampling exploration. We do some peat augering and sampling, and we bring back the samples to University of Malaysia Sarawak Geotechnical Laboratory for properties determination, and finally the conclusion. Okay. Okay, so for definition of peat, yeah, basically I believe that everybody well known on peat. Okay, peat is known as extremely soft and defined as a non-homogeneous deposit of partially decomposed vegetative matter saturated with water and encountered in low-lying areas. Is high compressibility and low shear strength, with recorded shear strength ranges from 5 to 35 kilopascal based on the in situ venture test. Okay, and in Sarawak, we can say that about 90%, okay, based on the literature, it's about 90% of the peat is classified as deep peat with a depth of more than 1.5 meters, and the depth of peat layers increases from coast towards the inland. Yeah. So if you can see from the right hand side table, these are the classification of peat, which have been extracted from the American Standard Testing Material 1990, Jared 1995, and also Quad 2011. So we can see that from the table here, peat can be classified based on the three types, okay, according to one post determination and as well as the fiber content determination from the ASTM, American Standard Testing Material D1997. So for the first type of peat is known as the fibrous peat, which is fall under category of H1 to H3 of compost scale. This peat has, if you can see the description, is mentioned that it's least decomposed. We can easily recognize the cell structure, and if you do some pH test, this type of peat is very acidic. And based on the fiber content determination, so under fibrous peat, they have about 67% of fibers. Then we move forward to the second type of peat. This is the hemic type, or also known as the semi-fibrous. This is the intermediate decomposed between the fibrous and also the separate type peat. Okay, and it falls under category of H4 to H5 for one post scale. and based on the ASTM, the peat has have about 33 to 67% of fibers. Okay, for the type 3, which known as amorphous peat or septic peat, okay, this is the highly decomposed with original plant fibers, has mostly disappeared, and the color is very dark gray to black, and this based on the fiber content, it is comprised of 33% of fibers. Okay, then we move to the next slide. Okay, here show the table summarize about the compressibility of the peat. Okay, compiled from Mastery 1997 and also Sadon 2016. So based on the natural, they're comparing the natural moisture content with the ratio of secondary compression with consolidation of coefficient of consolidation ratio for peat deposit. If you can see that based on the natural moisture content, okay, the higher the moisture content, I believe they have the highest ratio of secondary compression to coefficient of consolidation. And on the fourth column is presenting the researchers that been contribute in determination of this compression, the ratio of secondary compression and coefficient of consolidation. Okay, then we move to the next slide. Okay, this is the the site. Okay. So the first site here, we focus on the Balai Bomba Sri Aman. Alright, and we can see that, okay, from the figure, we the settlement of the infrastructure, okay, between the perimeter slab and the drain, okay, the settlement is measured in about 100 millimeter to 150 millimeter. Okay, and also on the right hand side, okay, you can see that the settlement observed at the car porch, right, at the car porch, and also at the perimeter slab. Okay, all the settlement measured at this area is in the range of 100 millimeter to 150 millimeter. Okay, and however, when we look at the structure itself, right, no obvious crack were observed in the main structure. Okay, in the area of Balai Bomba Sri Aman, it comprised of the main building and also residential and also the quarters for the staff. And from observation or for each of the structures, there is no sign of crack. Okay, in the main structure. Right, then we move to the next slide. Here is about we do some sampling. Okay, soil sampling exploration. Okay, for the to get some ideas on the on Sri Aman Peat. Okay, we do the augering. Right, if you can see on the left hand side, okay, a gentleman, right, a group of gentlemen is helping us to collect, to do the augering, to collect the sample. Okay, and we go for up to 2.88 meter depth, and the sample will collected at 0.5 meter interval, which is located behind the quarters, right? And all the samples were brought to the UNIMAS Geotechnical Laboratory for geotechnical properties determination. If you can see from the table here, okay, right? So these are the samples collected at each 0.5 meter intervals, and at the depth of 1.5 to 2.2 meter, we can see a clear vegetation on this being captured in the peat auger, right? And up to the depth of 2.3, okay, between 2.5 to 2.88, That is the depth of the pit, and the remaining of 0.3 is the soil, soft soil clay. This is the soft clay. So we can say that in this area, the pit is about 2 point up to 2.8 meter. Right, and then table here summarize the geotechnical properties determined in the laboratory for Sri Aman Peat. You can see the organic content for the site. The organic content, if you can see in the column that colored in red outline. It shows that the organic content for the site is in the range of 70 to 90% for a depth of 0.5 meter up to 2.88 meter. With the natural moisture content ranges from 900% to 1,400%. For the organic content, we determine it through loss of ignition test by igniting the specimen of the powdered material in a muffle furnace at temperature of 550 degrees Celsius, and the organic content obtained from the site as shown in the table. And for the moisture content, we do it based on recommendation from Scampton and Petley 1970. So we perform through using the oven dried technique at 105 degrees Celsius for 24 hours. And if we can see that the moisture content is very high, and this finding is in agreement with what 2004 and Matri Al-Uni 2007, which stated that the typical water content of peat is in the range of 200% to 2000%. So, and then we proceed with the one post classification. We can say that the peat is categorized as fibrous peat under category of H3, except for the first 0.5 meter, which fall under the hammock type, H5. This classification been done based on the one post test. And also from the table here, we can see the specific gravity. The specific gravity is the fifth column. The fifth column of the summary table. And we can say here that for the Sri Aman Peat specific gravity is in the range of 1.5 to 1.9 for a depth up to 2.8 meters. And this determination of the peat specific gravity for peat is based on the British Standard 1377, which we replacing the water by using the kerosene, due to the density of water density. And also we also determine the pH value. The pH value of the peat for Sri Aman we classified as highly to moderate acidic peat. This classification is been done through using or in accordance to American Standard Testing Material D2976, which is showing that the pH value recorded is in the range of 4 to 5. And then we the field vent shear test recorded. For the field vent shear test, we can measure up to a depth of 1.5 meter. The undrained shear strength recorded is varies from 10 kilopascal to 14 kilopascal. Then we move to the next page. Next slide. This is the conclusions of the findings that we've been done during our collaborative work in Sri Aman. So from the findings here, we can say that the settlement for the structures and infrastructures constructed on peat in Sri Aman, Sarawak is in the range of 50 millimeter to 150 millimeter. And the laboratory test conducted for the collected sample, the site has a high natural moisture content and organic content ranges from 900% to 1,400% and 66% to 95% for the organic content. Okay, and the Sri Aman peat is categorized as fibrous peat, okay, so highly compressible, except for the first 0.5 meter, which fall under H5, Hamic peat group according to the one post classification. Okay, I think that's all for the presentation today. About the modeling, we still looking for more laboratory data, because the one that we collected on the first visit is just sufficient for determination of basic properties. If you want to model the settlement or predict the settlement, okay, we need to perform consolidation test as well as the triaxial test. But this one will be in our second phase of the collaboration work. Okay, I think that's all. I would like to say thank you to all my team, okay, for the during the exploration, okay, and collecting the sample. Thank you. That's all.
Thank you, Engineer Dr. Naraslina, for the very interesting talk on Sri Aman Peat. Coincidentally, actually, I did my geological mapping in Sri Aman about 25 years ago. So
Okay.
I understand the situation in Sri Aman, and I have questions actually from the floor, and they were asking that I'm in the highway construction industry, mainly in Sarawak. We face a lot of differential settlement even after treating the soil. Any other method to treat the soil apart of R&R, PVD, and surcharge in the water? So
Okay. All right. Thank you for the question. Okay. And all the techniques mentioned is the common practice in Malaysia. It's common practice in Malaysia. Either R&R, we do PVD, or we do surcharging. Okay. But if you can see more with published work, okay, in other countries, they are introducing some kind of electrokinetic. Also, you can introduce stabilization on peat itself. Okay, but like I say, that is still under investigation. They are not using it at a very wide scale. But I believe one day this technique, okay, will bring especially the EKT, because to me, I'm very interested in electrokinetic treatment on peat, okay, because it can reduce the water and increase the strength of peat. Okay, so I hope that one of these techniques will be in Malaysia one day. So at the moment, to me, we can work for the stabilization. They have quite a number of stabilization techniques been introduced, like clay. They are using some kind of waste material using silica fume, and I think that can be done for improving the strength of the peat for long term. Okay, but how effective? So far, there is no evidence showing a long track record lah. Okay, because all this is just like try and error at the moment. I think that's all my answer for that, Mr. Jaisis.
And also I have actually two questions from Mr. Chiu. And one of the question he was asking is the photo shows the settlement of 100 millimeters. So what is the observed rate of those settlement? And and in how many years? I mean, for 100 millimeters, how many years does it take for this settlement? And the second question will be, do you perform 1D consolidation test? And what is the consolidation parameter? Example like CC, EO, CV, etc. for this need. Thank you.
Okay. All right. Okay. For the settlement, if you can, at the moment, if you can see the guideline from the JKR, they mentioned that the settlement, okay, in general, is acceptable for is between 100 to 250 millimeter, okay, in 7 years. So I believe, yeah, this settlement issue for is not applicable for Peat, so, because it's quite a large difference, okay, for between the normal type of soil and also the peat. But to me, this the one that been highlighted in JKR slope guideline, they mentioned that the settlement recorded, okay, is 100 to 250 mm lah. So I believe this is just my thought. So the construction itself actually is within the range. Just that is the soil itself causing apa tu, a large to a public is showing that macam attract dangerous to public lah. Tapi orang kata the settlement kan, kalau in the guideline is mentioned is in that particular range lah, 100 to 250 mm. Yeah. Like at the moment we don't perform any 1D or odometer test. Okay, we don't that's why we said that we need to go for the second, might be in future we need to go for the second trip lah, for collecting the sample to monitor, to get the CV value lah, coefficient of consolidation, and to predict whether the settlement will secondary compression will still continue, okay, for a longer period of time. I think, yeah, that's all my answer.
Yeah, and there is one more question again. Is ASOCA plot a more effective way to monitor the ground settlement?
The ground settlement.
Yeah.
Okay.
Using ASOCA plot.
ASOCA plot. Okay. I think in the instrumentation, I believe more on instrumentation. Okay, and then we can do the comparison with the ASOCA method lah. So far, not much instrumentation been done when we deal with this construction on peat. That's why we have a lack of field data. Okay, to field data to verify the one that we get in the lab lah. So I think instrumentation wise lah, we need to put some budget on it when dealing with peat. Hopefully the authorities lah can put aside on the monitoring. If not just the settlement plate, but some kind of quite extensive monitoring lah, for about more, might be in the range of 2 to 5 years observation, something like that. Yeah.
Okay. Thank you, Engineer Dr. Noraslina, for your paper. Very interesting paper, and I believe there is more questions from the floor. So once again, thank you, Dr. Noraslina, for your paper. Thank you.
All right. Thank you, Mr. Jaitis.
So the next paper will be given by Dr. Rauda Ahmedi, who is a senior lecturer at the Department of Civil Engineering, UNIMAS. She obtained her PhD in the field of civil engineering from the University of Sheffield, United Kingdom in 2014, and she is actively involved with the teaching and research related to seismic hazard and risk assessment and cement replacement materials. So with that, I would like to welcome Dr. Ahmadi, who will be talking about spectra, response spectra for modern seismic area and application to the Miri district of Sarawak. Miri.
Okay, thank you very much, Mr. Jayatish, Chairperson. Can everyone hear me? All right. Good afternoon, everybody. Assalamualaikum warahmatullahi wabarakatuh. I'm Rauda Ahmadi. Today I'm going to present and share to everybody on this research collaborated with the JMG Sarawak. All right, are you seeing this in full screen? Can you see it in full screen? Yes, okay, thank you. All right, Mr. Jay, this is just right next to me. I'm the moderator of this session anyway. Okay, so my presentation title is Response Spectra for Moderate Seismic Area Application to Miri District of Sarawak, Malaysia. So this is a jointly research between UNIMAS and JMG. From my side, it's me and student, master student Imtiaz Akbar. And also from JMG side is Mr. Thompson Gali. So as we know, in the past 20 years in East Malaysia, we haven't been facing much significant earthquakes. And everybody, I mean, the majority people know that Malaysia is safe from seismic earthquake hazard. However, as we know, in the year 2015, a very big event of Ranau earthquake with magnitude 5.9 happened, and that was the beginning of a very it's an eye opener for the government and for the whole nation of Malaysia. That we have to be aware of the condition of this natural hazard, seismic hazard that is coming to our country. So in the year 2015, an effort by the government to develop the national annex of Eurocode 8, which is for seismic hazard design, has been established, and it was completed. The document was completed in 2017. So, looking at the condition in our country, so this study I have been focusing for Sarawak itself, and in Sarawak, if we're looking at the whole map, seismicity map of Sarawak, we could see the highest the area which has a very high hazard is mainly located in the area in the Miri area. Yeah, okay, this is share probably slide. Okay, so this is the seismic hazard map of Sarawak. As you can see, I think most of the practicing engineers have seen this seismic hazard map that has been developed, and we could see the highest seismic hazard is in Niah area with 0.09 PGA for 10% probability of accidents in 50 years. That rate. Okay, so when we want to assess on seismic risk, for example, we would go for a higher return period, which is normally 2,475 years return period, corresponding to 2% probability of accidents. So normally this value 0.09 would go up to 0.15 G. So coming back to this record, we can see here, this is the earthquake histories that are recently happening in Sarawak since the year 2004, which we would say among the significant ones. The ranges of the magnitude, are between 3 to 5, 3 to 5. And we could see in Nia region, Bintulu and Miri region is having the highest earthquake magnitude so far. So that is the reason why this study we're trying to focus to the Miri district, knowing that this area is having a very vast development and a lot of resources of Sarawak in this region, and also because of a few active fault lines are heading towards this area. So there are several active fault lines here, like Tubal fault line. This is active, Tanggap Tinjar, and also Bukit Mersim fault line. These are the active fault lines. And we also have some inactive fault lines like West Baram fault line, Dengan fault line, Halajau fault line, Patau. And we do not know if these fault lines will remain inactive, because the progression of Earth continent movement, Earth movement, will eventually cause these fault lines to be activated in any time. So here, as I mentioned earlier, the predicted peak ground acceleration value in Sarawak is 9% G, 0.09 G for 475 years return period, and for 2475 we have assessed it to be as 0.15 G. Okay, so this is the graph again. In the code, in the national code, in the national annex Euro Code 8 for Malaysia, we did not produce the 2,475 years map yet, because it involves a lot of discussion. So at the moment, the government is only publishing, Department of Standard Malaysia is only publishing up to just 475 years return period, which concerns the existing buildings, not the critical facilities. So, okay, you see, site response analysis is actually part of the work or studies that is related to seismic hazard. So, in this case, when you wanted to do this kind of study, borehole data, which we say geotechnical data, is the most important primary data that we need to have in order to conduct such a study. In this case, for Miri region, we have 114 boreholes data managed to be collected, because as everybody knows, borehole data are not that easy to be obtained, because maybe due to confidentiality information. However, I can just assure everybody, when we are trying to conduct this kind of study, the borehole data are very important, and normally this data is not giving any harm, actually, in terms of this kind of study. It's not giving harm to the owner of those borehole data. I would pretty much advise or encourage consultants, contractors, and the owners of this borehole data to share most of the borehole data with researchers like us who do research, for the benefit of the country itself. You see, when we are able to produce, when we are able to conduct further study based on this borehole data, it would give us a lot of understanding on the current situation of the soil that we're having in our state, and therefore we could proceed with a proper land use planning, for future purpose, for the development in country. So as you can see in this slide, the distribution of the boreholes data, I would say, is actually random, and we have been trying our best to find as structured as possible of this borehole data to represent the findings later on. Okay? So on the right hand side, from the borehole data, okay, what we are obtaining is the shear wave velocity for 30 meter, for the top 30 meter, which we call as VS30. So this VS30 is the most important parameter that we need to obtain to proceed with the development of response spectra, so we could understand how much is the response of the topsoil surface, site response towards any seismic hazard coming into this region, specific location, for example. Okay, so on the right hand side, map in GIS, you could see the distribution of type of soil based on shear wave velocity. A majority of the soil in Miri district is under soil type C, D, and A. Yeah. So we are using Imai and Tanishi relationship to get the final values of the S, and from there we use the HERB relationship to produce the VS30 values. Okay, so this is the classification of soil type based on the HERB. So from the analysis, from the site response analysis, we are able to obtain amplification ratio information, and also predominant frequency. We could also get response spectra. The next slide. So you see here it says in designing structures on soft soil, it is very crucial in including the site amplification, as it is where the seismic waves amplitude grows, especially as they progress through the layers of soft soils close to the surface of the earth. So this is the supervisor which manipulates the size of construction on structures later on should there be any earthquake happens. Yeah, and yeah, the amplification ratio also is also one of the important factor that raises the peak ground acceleration from the bottom bedrock of the ground. Yeah. So the findings in this study shows that in Miri district, the ratio of amplification ratios varies from 2.16 to 4.79, especially in the southwest portion of the district, being greater than you see, look at this here. So the predominant frequency and amplification are both significantly affecting the harm, which caused by an earthquake to structures. These two factors. Okay, so in this slide, I'm showing to you the analysis they carried out for the 114 local data, and we've been applying earthquake response to each boreholes and checking on various PGA input, especially focusing on the 2% probability of accidents for 2475 years of return period. On the right hand side is actually the response spectra for 5% damping for Sarawak itself, which is according to the Malaysian National Index. Okay, so we do comparison and wanted to see if our site-specific data would match with the one proposed in National Index for Malaysia and for Sarawak specifically. Okay, so this is the results of the. This is on the first figure is for site C, site type C, site type D, and also for site type E. Okay, so we will be this response spectra shall be used by the shall be used by the structural engineers as an input data to assess on the seismic response of the new building designs or any existing building. Check on the capacity of the current building. Okay, so further from this response spectra analysis, we have carried out another study, another factor to study, which is liquefaction analysis, because this liquefaction factor could be obtained also from just the geotechnical data, borehole data, SPT level data. So in this case, I'm trying to share with everybody where this response spectrum research is heading towards. So in this study, we are trying to head towards the land use planning to see how the existing land use planning is matching with the seismic microzonation map that we produce from this study. Okay, so we did on liquefaction analysis, checking on the liquefaction potential index, checking on the factor of safety, and the two maps here on the right hand side and on the left hand side are showing the liquefaction potential index and also minimum factor of safety. Right. So proceed from this. So from there, we produce seismic microzonation map for Miri district with 5 factors involved, which is the peak ground acceleration from seismic hazard, PS30 factors, liquefaction potential index, amplification factor, and also predominant frequency factor. So mixing this in the based on weightage basis scoring using AHP method, we are able to produce seismic microzonation map of the whole of Miri to show the severity of seismic hazard in this region. So you could see in the map here showing the northern part is having a very low hazard. Some parts here are having moderate and some parts are with high specificity. Okay, so the northern part Miri district is under low hazard. Majority of southern and central part is moderate. Some parts are high. Okay, so we proceed with our aim to understand whether the seismic hazard, how does the seismic hazard here in Miri matching with the current land use of Miri, and also we wanted to give future advice looking into the future aspect of land use planning for Miri. So we compared with the current land use map of Miri, we can see this are shown in the land use map of Miri. In this table here, what does it mean by when we divide the seismic microzonation area into 4 sites: site A, B, C, and D. We divide it into site A, which is having low PGA, very low liquefaction potential, and also low amplification factor. So site B, site B. So it has a moderate PGA, slightly higher than the lower area. Moderate liquefaction, potential moderate amplification factor. And for site C, it's having a high PGA, high liquefaction potential, and also high amplification factor. Finally, for site D, this is the very dangerous area where it is the fault line area. Whether it be active or not active, we are classifying it under fault line area. Okay, so from further analysis, we have come out with suggestion based on the sites. This is the results showing for agricultural land, site A is suitable, B is also suitable, C suitable. All sites are suitable for agricultural land. But when it comes to commercial aspect, only site A and B is suitable, but C and D is not suitable for this purpose. So it same. So for the rest of the factors, we consider residential area, villages, emergency, educational, and also industrial. Yeah. Right. So this is the final, we come up with a final proposed land use planning just to ensure that the current state of seismic hazard in Miri district is understood by the government and everybody. Okay, so we have here high density all built out zone. It's a yellow area, so we can build residential area definitely here, commercial area. We have moderate density all built out zone. We can still have commercial area and also residential area here. And then we have agricultural zone. Agricultural zone is orange. So small south area of Miri. Dockyard zone, fault line area zone, which is not permissible to put important structures there. I also wonder about this here. Okay, right. So as a conclusion, trying to emphasize that the usage of this spectra from Miri districts is significant in order to develop land use planning on the basis of seismic micro-resolution for the state of for Miri district. And I would say this is kind of a first study has been carried out for the state of Sarawak. We could extend this for other areas, other important areas, to just ensure that we are on the right track for land use and land use planning purposes. Okay, so yeah, I think that's all for my presentation. Give this session back to Mr. Jaidesh.
Thank you, Dr. Rauda, for that talk on the response spectra for the moderate seismic area. I'm sure some of you who are listening to this speech might probably be, feeling uneasy, when they hear about fault line, about seismic, all these things. But let's be clear about it. That, no one actually knows when when can happen, where or when. So this study is actually, as what Dr. Radha mentioned, is one of the first to be carried out in Sarawak, and we hope that this will be just the beginning of many more research in Sarawak. So with that, I would like to open the chat room, and I'd like to invite questions from the floor. Okay, I have one question. It says that our current project is located at Lawas. The seismic loading adapted for our design was 0.05 G. However, the recent earthquake incident happened in the north side of Borneo Island. Triggers us if we really need to reconsider the adoption of 0.05 G or vice versa. Our neighboring country, Kalimantan, is adopting 0.075 G. So, Dr. Radha, you can,
Okay. Yeah, thank you, Mr. Jaidesh. Yeah, and thank you to Mr. Manian Rama for this question. Yeah, I agree with you that Lawas is having 0.05, and that is for 475 years return period. Yeah, so meaning if you are to construct a higher important structure, you have to go for 2475, 2,475 years return period PGA. Okay, when we said that there's a recent Kalimantan, there's a recent incident happened in the area toward the north, yeah, I think the northern area of Lawas. Normally this area we could, they are having like frequent seismic threats. Yeah. Okay, so I would say the best is, of course, we go for a higher PGA for design. At 0.075 is a fair value for 4753 period design in Sarawak. Because if we read more papers done by many researchers, one of the prominent one is Professor Nelson Lam. He mentioned that for Sarawak, it's best to put 0.07 G for our minimum seismic design for structures. It's just that when we produce the national annex, they are
very environmentally friendly, actually. Very green.
Sorry about that. Also, all of us are in the same room. Okay, so Professor Nelson Lam suggested that for Sarawak, that's the whole region of Sarawak, he would suggest that the whole region is taking 0.07 G PGA for a design. It's just that we don't want to make it compulsory to all regions when some regions are really having small, very, very small seismic hazards. So for Lawas area, it happened that this area is sometimes prone to seismic threats from our neighboring country. So in this case, if you think that you want to go for the best design safety factor design, 0.075 is fair to be taken as the design PGA. Mr. Malia's specific guideline to refer is, of course, at the moment, the National Annex. National Annex 0.8, produced by the Department of Standard Malaysia. Yeah. But if you want to go for a better design, 0.7 is proposed by other researchers too.
Okay, thank you, Dr. Rana, for that information. Regarding the seismic area, as we all are aware, actually, North Borneo is currently one of the areas where lately a lot of research have come out, especially after the Sabah, the Rana Kundasang earthquake. So that also actually triggered the Sarawak side also to do the studies. I think hence Dr. Rauda is involved in this project. So I think we would like to see whether there are anyone from the chat room, anyone have any more questions to ask. Okay, if with that, I would like to thank Dr. Rauda for her talk, and thank you very much.
Right. Thank you very much, Mr. Jaidesh.
Okay, so with that, we will have a break now for our lunch break, and we will start at 2 o'clock sharp. Thank you.
Maybe that's one quick question for people of the council.